My name is Dr. Fred Vandeman. I'm an interventional radiologist. I've been in the field for about 37 years, and I retired about 3 years ago. I came back to evaluate this project as a consultant, to give some opinions on where we were going with the project, and to see what factors need to be applied to this equipment to provide adequate ventilation based on the medical requirements.
My name is Dave Poole, and I've been working here at Phoenix America for about 6 years as a principal engineer. My degree is from Purdue University in electrical engineering technology, and I've been designing controls and machining, and I do a lot of electrical work, and I do some computational work and a lot of design work, and even fabrication of myself on a lot of this equipment. So here we are in Fort Wayne, Indiana today, and we are demonstrating a sort of a triage respirator machine. Initially, we were looking at just supplying components for the machine. And we actually are doing that today, but after we saw a couple of the designs, we thought that it would definitely be within our capability to actually design and manufacture the machine here. So we continue to work with other actual ventilator suppliers to supply them components, but now what we've done is designed our own up, and this is inspired by a program up in the University of Minnesota, and we kind of got involved with it fairly early, and the whole idea there was to demonstrate a concept and then sort of put it out there for guys like us and companies like us to look at and say, yeah, we think we can make something like this, and we think we could do it fairly quickly and scale it up. So you'll actually see there are similar kind of designs like this if you look out on YouTube and so forth, but each one will be a little bit different. And what we did with this particular design was we kind of tailored it to what we know best, the kind of motors that we generally would use, and the type of control components that we would generally use, the type of fabrication that we can typically do, and most importantly, how quickly we can make all that happen. So we can't pick a motor, for example, that is not available on the shelf today. So those were just some of the design constraints that were put into it. The principle behind the design here is we're simply pushing on what they call an AMBU bag. And the AMBU bag is what's actually supplying the air to the patient. And part of the project, as we started looking at things, it would be a lot less complicated and we could get to market a lot quicker if we just focus on the control of pushing on this bag and then leave the bag and the plumbing and the lines and so forth up to what's out there available in the market today, because these components actually are pretty readily available today. So what we have here is we have a simple DC permanent magnet motor that's turning, and it's turning at anywhere between about 1,000 and 1,500 RPMs. And it's actually turning a small gear reducer, and that gives us the right speed for the patient. And we can change the speed of what we call the breaths per minute. Right now I just have a simple dial on the top here to demonstrate that. But in our next version, which will be our final ready to go version, we're actually designing right now and working on, we'll have a control board in here, and the control board will give us very precise control of the whole stroke, because when we breathe, we don't just breathe in this normal cycle. We actually, we inhale and then we exhale, and that inhale typically is takes about a half as amount of time as the exhale does. And that's something that with the ventilator, they like to be able to control that. The rest of the components here are just, these are just standard off-the-shelf rods and linkages, and a small bushing and a steel rod. And this part here is it's just a plastic interface that's pushing on the bag. Dr. Vandeman actually printed that for us and delivered it to my home on Sunday as I was actually building this prototype on Saturday and Sunday in my own shop.
During the current crisis, we're confronted with an ever increasing number of patients. As the number of cases ramp up, we can see critical shortages of medical equipment and personnel in cities like New York City, which will spread to other portions of the country. The requirements for ventilation equipment are rather critical, and there is a fear that we may not have enough ventilators to supply to correctly treat the patients. And if we don't, then we'll have patients that will not be properly treated and could expire without having the equipment to treat them. I'd like to make an analogy. If we have, for instance, 100 patients in our hospital that have COVID-19, in that 100 patients, the majority, probably 60% or more, will have disease that doesn't require a ventilator at all. Those are fairly moderate cases, but they still require admission to the hospital. If they have some insufficiencies, they may be able to compensate with cannula oxygen or maybe a face mask oxygen, but they don't require a ventilator. The other subset of patients are those that actually require a ventilator. And if our hospital has 25 ventilators, for instance, and we have 20 patients, we're okay. We don't have a problem. Every patient gets a ventilator. But as our casualties start to increase, we may find that tomorrow or even the next day, we have 30 patients that need a ventilator, and we only have 25. We can't get more ventilators from the government or other facilities, and we have 5 patients that we can't offer a ventilator to. We're going to have patients die in that situation without the proper treatment. This device can act as a bridge to make ventilators available to the sickest patients. If we have that subgroup where, say, 25 patients need a ventilator, probably only about 10 of those patients are so severely ill that they need a ventilator that has all of the bells and whistles of the best ventilators that we have. Those patients will definitely be placed on the ventilator. If we can free up more ventilators by using a device like this, we can supply them with adequate ventilation and still be able to supply the correct volume, the correct rate of inflation. We can supply heated air, humidified air, and we can vary the pressures that are applied by our tubing circuit. The tubing circuit actually takes the oxygen and air from one end of the bag and through valves and tubing delivers that to the patient. When we're compressing the bag, that's during the inhalation phase, and you can see here that causes the patient's chest to rise with every breath that we deliver. And then the air circuit that we have is based on equipment that every hospital has. And that's not something we need to provide to them. They have that available for their ventilators. All we would have to provide is a means of compressing the ambu bag at a rate and to a depth that produces the correct amount of the volume of air that's needed or oxygen that's needed and the correct pressure. The pressures can be managed by valves that are placed in the circuit so that we can adjust the pressure that we're delivering. And then our machine has an adjustment here where we can move the bag up and down. We can vary the speed of the stroke so we can go to a point where we're offering more rapid ventilations, or we can slow that down in patients that don't need that. And in some patients, the disease progresses to a point that they develop ARDS or ARDS. And when that happens, the lungs become less compliant. They won't accept the pressures that a normal lung would. And if you deliver that pressure to that lung, you can damage the lung and end up with complications that are far worse. And so that's where we rely on the circuit that's provided by the hospital to be able to adjust the pressure. When we're delivering breath to the patient, we have to be able to vary the amount of pressure that's given. In patients with ARDS, the lungs become far less compliant, and the same pressure delivered to a patient who has ARDS may damage the lung or perforate the lung in a way that's detrimental. So we have to limit that pressure, and we can do that by a number of valves. For instance, you can see here on this valve that every time our ventilation approaches the red zone or the danger zone, the valve in the line bypasses the circuit to allow air to escape through the valve. If I close that valve off, you can see the pressures now are very much in the red zone, and that could damage the patient. So those type of things allow us to use the standard ventilation circuit and tubing that's present in the hospitals to maintain the proper pressure and to maintain the proper airflow and tidal volume, or the total amount of air that's going into the patient. As we've been evaluating this equipment and the potential use of this type of equipment, I've reviewed the equipment with two of our physicians at our emergency care unit at one of our local hospitals. These are pulmonary specialists that deal with the COVID-19 patients daily, and they understand the consequences of having ventilators available and some of the complications that are involved with patients as they become more and more ill, or as their pneumonia from the COVID virus progresses into ARDS. That can produce very severe problems. This type of equipment can be utilized to treat a number of those patients with somewhat less severe disease, but disease that still requires ventilation support. And if these units are used to provide that support, that frees up the full ventilators that have all of the bells and whistles for the patients that are more critical and need that assistance immediately. One analogy that was made by one of the physicians that I consulted with basically said, if he has an auditorium full of critically ill patients and he has only so many ventilators available, and the consequences of not having enough ventilators available becomes critical to the point that he has to provide support for these patients, this is the type of unit that can be used. All of the patients that require ventilation, even the patients that can receive that ventilation with a unit such as this, need to have it delivered in a safe way with certain limitations on pressure and volume, and that's what we're building in with the circuitry and the tubing that we have in-house at our hospitals.